This is the measurement in analytical chemistry. It is another textbook, but it contains similar information as the Harris's book. So, because the analytical chemistry is a quantitative science, it deals with measurements. And when we deal with measurements, of course, we have quantities. We have number associated with a unit, or unit associated with a number. But when we use different units for mass or for weight. For example, we use pounds, we use ounces in the United States. This is English system, of course. We also have metric system like grams. But in the scientific community, in scientific publications, we always use the metric system, SI units. Even in the United States, our daily life, we use metric system, we use English system, but in our publications, we use SI, International Unit System, SI units. And there we have 7 base units in metric system, in SI units. So one is mass, the unit is kilogram, symbol is kg, distance, temperature, time, current, amount of substance, and light. Those are the base units. All other units are derived units. As you see here, we don't have the liters or joules and other speed, for example, because those are derived units. So here you see some of them, liters, for example. That is the 3 distances multiplied. So it is meter times meter times meter times. So you come up with cubic meter. The force is meter times kilogram divided by second squared, and so on. And joules. So you got the combination of several units, base units. So you come up with a unique derived unit. Now, along with the units, of course, we have prefixes, and the prefixes is to make numbers easier to handle. For example, a mole of any substance contains this huge number. There are many zeros there, 20 plus, yeah, I mean, including number. So there are many numbers here. That is a huge number. So when you write it down, so most of the time we try to count them, make sure we're missing any zero, or we're not adding more zeros. So it is really challenging to handle those numbers. So this is another small number. So there are some techniques, analytical techniques, that can detect this gram of a compound or a substance. Now, and to make it more, better or easier to handle the number, we use scientific notation. Scientific notation is basically we use those zeros, we use exponential part. So you have, instead of this 6.02313 and so on, the huge number, we use this one with 10 to 23rd exponent, the exponential part. And in most cases we use only 6.022 10 to 23rd, so we kind of ignore this part as well. And the other one is 1.10 to negative 15th. That means, so you move the decimal point to the right until you come after 1. So because in scientific notation the number has to be between, we call it significant, the significant has to be between 1 and 10. It cannot be smaller than 1 or greater than 10. And that is what we have. And we got common prefixes that are used in scientific community here. I mean, everywhere actually. And so the prefixes, they start with iota. up to, well, down to iota, and iota is iota through mega. Those seven prefixes. The symbol is capital capital letter, and all the rest of the prefixes are lowercase, as you see. So we got 10 to 24th down to 10 to negative 24th. So that's tiny. It's very small. And one way of memorizing or keeping these prefixes in mind is mnemonics. So here we got one. Young Zach earns pennies to give mighty King Henry's daughter Beth, who drinks cold milk until 9 p.m. for a zillion years. So you see, those are prefixes that we have, the common prefixes, and the like 10 to 24th is the exponential term that can be substituted for y, the iota, or vice versa. For example, one iota second is 10 to 24th second. So instead of 10 to 24th, we can put capital Y, or instead of capital Y, we can put 10 to 24th. So those the Y, we substitute Y for 10 to 24th. The other example is megagram. So mega, as you see here, is 10 to 6 million. So 7.2 megagram equals to 7.2. We substitute M. We substitute with 10 to 6. So because those can be substituted for each other. And 3.7 10 to negative 15 liter. 10 to 15 is femto. So we can substitute that for F for 10 to negative 15. So those are if you get rid of, if you want to use the exponential, we just remove F, we put 10 to negative 15, or vice versa. And so these are equalities. For example, 1 nanometer is 10 to negative 9 meter. Nanometer means if you have a meter stick, you slice it into a billion even slices. So each thickness is 1 nanometer, and it is so tiny. And so that means 1 meter contains a billion nanometers. So that equality, we can use it as conversion factor, as you see it here. For example, if we want to convert 280 nanometer to meter, so we start with 280 nanometer, and then we use conversion factor from the table. Of course, here we got it. 1 nanometer is 10 to negative. So our goal is to cancel out nanometer, end up with meters. So to do so, we have to put this in this equality, the nanometer in bottom here, denominator, and meter on the top, and they will cancel it. So we come up with 280 10 to negative 9 meters. And in scientific notation, because the number has to be between 1 and 10, we have to move the decimal point from here after 0 to between 2 and 8. So you have to move decimal point to the left twice. That means you will put plus 2 because you move to the left. That means if you are, we are making 280 smaller, like 100 times, from 280 to 2.8. So you have to increase the exponent here, and it becomes 2.80 10 to negative 7, because negative 7 is greater than negative 9 meters. So that's how you can apply that to any conversion. So as long as you have the conversion, the factors here, the conversion, we can use those as conversion factors to do the conversion between the prefixes. Now, whenever we have measurements, always we have uncertainty associated with the measurements. For example, if you are using scale to measure a substance, and you see the fluctuations within seconds. So 0.5729, 0.5731, 0.5730. So if you take the average of those three numbers, it is 0.5730, and so when you take the average and find the error, standard deviation, it is 0.0001 grams, meaning plus minus means the number is not exactly 0.573, but it is between 0.5729 and 0.5731, so it is between there somewhere. So the last when we report a result, so when we result a value, a measurement, we always keep the significant figures, the certain numbers plus one uncertain number. So the last number is always, it contains some uncertainty. So significant figures is basically, it tells you how much certain the number is, and so that's why in this number 0.5730 we got 1, 2, 3, 4 sig figs. We got 4 significant figures, and the last digit is significant, but it is uncertain. But the other numbers are certain. We're sure about the other numbers, 0.573, but the last digit contains uncertainty. And when we convert, for example, if we use the same scale and measure another substance that weighs 0.0990 grams, as you see, we got 1, 2, 3 sig figs. So the initial, the first zeros are insignificant because they are there to show the decimal place, where the decimal place is. And when you write it in scientific notation, you write it in 9.90 10 to negative 2. So as you see, we got 3 sig figs. Okay, that is, and so zeros that come before non-zero, they are insignificant, as we see it. We explain it here because those zeros are just to show the decimal point, where the decimal point is. So here we got 1, 2, 3 sig figs. In 605.3 milligram calcium carbonate, we got 1, 2, 3, 4 sig figs. In 1.043 10 to negative 4 moles of silver ion, we got 1, 2, 3, 4. There's 4 sig figs. We don't worry about this exponential here. In 9.3 10 to 4th milligram sodium hydroxide, we got 2 sig figs. These are what we remember from general chemistry, and we can add the log. So in such as like when we have pH is negative log of hydrogen ion concentration. The number of significant figures is equal to the number of digits to the right of the decimal point. So for example, a pH of 2.45, 2 is not significant, only 4, 5 are significant, because that 2 indicates the power of 10 only. So it has 2 sig figs. And also we got exact numbers. So exact numbers, they might have many or infinite sig figs in that. So that's why when we do the measurements, we want to make sure we report the correct error associated with our measurement. For example, if a balance that measures mass to the nearest plus minus 0.1 milligram, and we need to report it as 1.7623, because 0.1 milligram is like 0.0001, so the uncertainty is at the 10,000th place, and 10,000th place is here. Now if you report it as 1.762, so you're reporting the uncertainty at 1000th place, so that is not correct, it is incorrect. If you show your number like 1.76231, then you're telling people that the uncertainty is at 100,000th place, which is not correct. So we have to watch for those. And significant figures in calculations, if we're adding or subtracting the numbers, we have to watch for the one that has least sig fig after the decimal point. So just imagine we got three different different scales with different sensitivities, and one can measure only 2 digits after the decimal point. You can weigh only 97.33 grams. The other one, you can have 3 digits after the decimal, so it is more sensitive. And so the last one is even more, is the most sensitive among those three. So, but when you if you measure 3 samples using those 3 different scales, then you will have to go with this one, because if you report greater than more than 2 digits after the decimal point, you assume that this is sensitive as the other ones, which in reality is not. So that's why you will have to report your answer. Your answer should not have more than 2 digits after the decimal point. And the same applies for the subtraction. And here, if we're dealing with scientific notation, for example, we want to make sure the exponents are the same. You see 6.17, 10 to 7th, 4.3, 10 to 5th, and the last one's 3.3, 10 to 4th. And because those exponents are not the same, we have to make them same. It's like adding apples and oranges. We cannot do that. So the first thing we do is to make the exponents common, make sure all of them are the same. And to do so, we have to play with the decimal point. We have to move the decimal point. If we want to keep the 10 to 7th exponent, then we will have to change the we will have to play with the decimal point in the other numbers. 4.3, 10 to 5th. So you will have to move the decimal point to the left twice. So if you move twice, you will add +2 to the exponent. So again, remember, when we make the significant, this number smaller, the exponent will have to get larger. So here, by moving 2 decimal point, we're making 4.3 100 times smaller. So you will have to make the exponent 100 times larger. So you add 2 zeros. That's 5.2. So you come up with 0.043 10 to 7th. And do the same thing for the other one. So you will have to move the decimal point to the left 3 times, so that you come up with exponent of 7. And then once the numbers exponents are the same as you see it here, then you can add the numbers. And look at the numbers here. 6.17, there are 2 digits after the decimal point, and the other has 3. This has 1, 2, 5 sig figs after the decimal point. So our answer cannot have more than 2 decimal point. So when you add them up, you get, your calculator will give you 6.2163 10 to 7th. So we keep this a common. We keep one exponential part, and here, because we cannot have more than 2 significant figures after the decimal point. So so this 1 here shows that is the last digit that we can keep. But because we got 6 after that number, that will round it up. So your answer is 6.22 10 to 7th. So when this is addition and subtraction, of course, when we deal with the multiplication and division, now the rule is different. Here we look at the whole number, and the number that has least sig fig is our reference. For example, 22.91 times 0.152. So the first number has 4 sig figs, the second one has 3 sig figs, divided by 16.305, which has 5 significant figures. And so your final answer cannot have more than 3 sig figs. However, before we get to the last step, we want to keep 1 or 2 additional uncertain numbers so that we don't come up with the error because of the rounding off the number. So that's why here when you multiply those two, you get 3.48232. So we can that is fine. That is fine because the calculation is not over yet. So ideally, if you stop there, if you just multiplication, if you're just doing that multiplication, then you will have to keep 3.48. But because we have division left, we keep a 2, or this 2, the second uncertain number, or the third, and then after we divide it by this, because we know that the answer cannot have more than 3 sig figs. So we divide those two numbers, you come up with 0.213613. So again, what was our rule? We cannot have more than 3 sig figs. So 0. That's not significant. 213. So that's those 3 numbers that we have to keep. But because the number after the uncertain digit is greater than 5, it will round it up. So your answer will be 0.214. Yeah, those are basically yeah, we have to retain more when we do the calculation, and so on and so forth. Now this is an exercise here. It is more complex. So we got two numbers, 0.250 times 9.91 scientific notation 10 to negative 3 minus 0.110 to times 10 to 1.927 10 to negative 2 divided by, so you got two numbers that we have to add. And the solution, if we look at the solution here, you see we have to take care of the first one, for example, here. So when you do those two, you keep the exponential the same, so 10 to negative 3. So you just multiply these two numbers here. The significance of those, well, this is significant of this scientific notation, and that will give you 2.482. Now ideally you should have 3 sig figs, because both of them, they have 3 sig figs, but here we keep one more to the end. So when we come to the end, this is where we decide the numbers. But here 3 sig figs. Now in this operation here, that is we got 3 sig figs here. This is not significant. In hundreds, 0.100, so there are 3. Here we got 4, so your answer here cannot have more than 3. But we keep one additional digit to be safe, to be on safe side. And of course, because this is 10 to negative 3, we want to make sure we play with the decimal point to the left or to the right, so that the exponent is the same. The same is here. Here it is not. We haven't made those converted those exponents yet. But if you look at here, after we take care of it, because the exponents are the same, 10 to negative 3, the denominator, numerator there, numerator, then we do the math. So you come up with 0.555 10 to negative 3, and so we can convert this bottom number to here we can do either way, 10 to negative 3 or 10 to negative 2, depending on. If you want to make 10 to negative 3, we will have to move this decimal point to the right. So it will be 9.93 10 to negative 3 plus 19.27 10 to negative 3. But we decided to go with negative 2. So in that case, you will have to move this decimal point to the left, 9.93. So you make it 0.99, because you moved one to the left, once to the left, then you will add 1. So negative 3 plus 1, and so you come up with negative 2. And now you see you got the same exponents, and that one. And then you can go ahead and add those two numbers, these two numbers up, and you come up with 2.920 10 to negative 3. And so you divide those two numbers as you do regular numbers. The exponents here, the exponential part, it will be 10 to negative 3 minus, open parentheses, negative 2. And so that is basically, of course, the number that you get it here, and after doing this operation here, the top minus the bottom, the exponent, you come up with 1.9 10 to negative 2. That is your answer. Now the concentration, I will make another video. I don't want to spend too much. Don't want to make this video too long, so let's stop here and for the second video, hopefully.